Hello and good morning to all of you. I, Anand Ranjan, Assistant Professor, School of Computer Application, Babu Narsidas University. Welcome you all in the video lecture series of Digital Electronics. In this video, we are going to learn about the combinational circuit design. So, with this topic, combinational circuit design is we are considering in our module 2, and we'll start our discussion with a general procedure how to design a combinational circuit, and this will help us to understand the upcoming combinational circuit designs. And for most all the combinational circuit design will follow the same design procedures. So it become very important to know initially that what are the fundamental design procedures to make our combinational circuit logically as well as on circuit level design. So the general design procedure is to, first of all, we have to identify our, these are the design procedure, means first of all we have to identify the inputs and outputs. Then we have to construct the truth table based on the system operation. After that, obtain the Boolean expression of the output in either the sum of minterm or the product of maxterm form. Then simplify the output expression using either the K-map or the Boolean algebra. And finally, the reduced Boolean expressions will be implemented using the digital logic gates or basic logic gate. So this is the fundamental block diagram of a combinational circuit, in which in this side we are considering the n input variables, and on the other side we are considering the m output variables. So we'll start with the first combinational circuit, which is the half adder circuit, and of course this half adder circuit is used to add 2 bits only. And in this half adder circuit, we represent here the block diagram of a half adder circuit, in which there are 2 inputs x and y, which will be uh, um, known as 2 inputs known as one augment and another is the addend. And of course x and y will be either 0 and 1 in binary domain. And based on this half adder summation, we might have 2 outputs, in which one output is sum and another output is carry. Okay, one output is sum, another output is carry. So overall functionality of this half adder circuit will be summarized using the truth table. And in this truth table, we are considering x and y as the 2 inputs, and s and c, that is sum and carry, will be considered as the output variable. So with the input variable x and y, we can generate 4 different combinations, and these combinations are 0 0, 0 1, 1 0, and 1 1. And the sum column will be based on the magnitude sum of these combinations, and which can be represented in S column like this. So for example, if you add 0 and 0, though, you will get 0 and no carry will be generated. So we will write it as 0. And then for the combination 0 1, if we add 0 and 1, we will get sum 1, no carry is there. Similarly 1 0, sum is 1 and no carry. And finally the 1 1, in which of course the addition is 2. So at the position unit position, you can say you will get 0 and you will get 1 carry at the output. So this truth table actually completely functionalize or completely characterize the half adder circuit. And based on this truth table, these are the output columns you can assume: the S column and C column, that is the sum column, and carry column. And for these column, you have to write the Boolean expression. So this output expression which we are written over here, in which if we have to write either the min-term approach. So we are following the min-term approach, means for write the ones present in the S column, we write this expression S is equal to x bar y and x y bar. So this is the S expression, some expression, and of course this is a standard output, so we can write S is equal to x bar y, x bar y, sorry, S is equal to x XOR y, x XOR y. Now look at the C column. If you look at the C column corresponding to the input variable x and y, then you can see this is again represent one standard uh, gate output, means that is AND gate output. So you can write that the C is equal to x and y. C is equal to x and y. So these two expression, S is equal to x XOR y and C is equal to xy, represents your output expression for the half adder circuit. And now with this two small Boolean expression of the half adder circuit, you can implement it using the basic logic gate. So as you can see that we have inputs x and y, and that these S expression and Y expression required only two gates, means one XOR gate and one AND gate. So these are the inputs x and y, which represents vertically here, and we use one XOR gate in which the inputs are taken from these input variables x and y, and so that the output S is generated, which is x XOR y, and C, which is carry, which can be implemented using one AND gate, because C is equal to xy, one product term is only there, and so that we are using two input AND gate, and with this two input AND gate, inputs are x and y, we will have this C implementation of for the C expression, which is x is equal to y. So this is the circuit diagram, or the logic diagram, or the implementation diagram, we can say, for the half adder circuit. Now let's try to discuss the full adder, another combinational circuit, which is the full adder circuit. And of course the full adder circuit is used to add 2-bit, means 2-bit, considering the carry from the previous stage, or in other word we can say that for performing the multi-bit addition we are using the full adder circuit. Okay, so the multi-bit addition concept will give us an idea to make this kind of block diagram in which the inputs are x and y, and we are considering the previous carry in as an input in this full adder circuit. And on the output side we have S, which represents the sum, and the C out, which represents the carry out. One more representation of block diagram representation of full adder circuit can be represented like this, in which x and y represents two input, and this is the C in, which represents the previous carry in if it is initiated, and the two output, we are having sum as well as the C out output generated by the full adder circuit. So again the overall functionality, and just we have told that there are 4 standard procedure to analyze any combinational circuit, in which first of all you have to identify your inputs and outputs, then you have to write the truth table based on that input output and the input output variable, and finally you have to write the Boolean expression for the output, and then if it is possible to reduce it using the Karnaugh map or the Boolean algebra concept, if you reduce it, and finally that reduced Boolean expressions will be implemented by the basic logic gate. So here we have decided these are our inputs, means x, y, and c are our input, and the S and C out are our output. So if we write this x, y, and c in here as an input variable, and C out and S as our output variable. Okay. So of course, for the sake of simplicity, we generate with the 3 input x and y, x, y, and c, and we write all the possible 8 combinations in this fashion, and which will help us to imagine that if the two combination like this x and y having previous carry or not. So for example, if we are adding x and y means 0 0 with no previous carry, then the sum is 0 and carry out is 0. Similarly, the second in the second page, the second row, what we are assuming that the inputs are 0 0. So if we add inputs 0 0 with previous carry input 1, so in that case what happened that the sum will be 1 but no carry will be original. In a similar fashion, we actually write the whole operation of these bits with and without previous carry, so that we will have the SC out column and the sum column in this way. Now, finally, in the next step, we have to write the Boolean expression for sum and Boolean expression for carry out. So again, we have to look on these columns. Means if we look at the sum column, then wherever we are having 1, the corresponding minterms will constitute the S expression. So we write S is equal to sigma M 1, 2, 4, and 7. This is the compact form or the minterm representation of the sum expression. Then similarly, we write the Cout expression like this as sigma M 3, 5, 6, and 7. So we have at all these three expressions, and of course we can also write in the standard canonical form these S and Cout expression in this way. Further, we try to reduce these unsimplified Boolean expression using the K map. So, of course, we have seen that S and Cout, these two functions or these two, which represents one Boolean expression, which is a function of three variables X, Y, and Cin. So, we require three variable K map, means 8 cell K map is required to simplify both these S and Cout expression. So, here we draw the three variable minterm map, we can say, in which inputs are X, Y, and Cin. So on one side we are considering X, and on the other side we are considering the remaining two, Y and Cn. So then of course every cell of this map is represents the corresponding minterm. So and on the corner of these cells we write the decimal equivalent of that minterm, which will help us to speed up the entire process of mapping as well as grouping of the adjacent cell and to get the reduced Boolean expression. So the first map is for sum, and this is the second map is for the Cout we made here, and we map all the minterms inside this map to get a reduced Boolean expression for S and Cout. So first, when we map the S expression, then we can see that there is no means adjacent cell can make a pair, means no pairing can be done because the minterms are on the diagonal side, and diagonal pairing is not allowed in the Boolean K-map simplification. So we can say this this map is not going to help us to get a reduced Boolean expression, and we will further see that whether we'll take help of Boolean algebraic concept to get a reduced Boolean expression. But at the same time, when we map the Cout expression in the K map, then we have some pairing with the adjacent cell. So we have got three pairs with the adjacent cell, and when we make groups of with the adjacent cell, we get this Cout expression as X is the Cout is equal to XY, YC, and X. Further, now let's try to get reduce the S expression. So first we write the standard canonical form expression, then we'll take some variable common in like Cin and Cin bar. So we'll get these expression, and these are the standard gate output expression. So we'll write those expression in the form of the symbolic form which represents these operations. So like this Cin and X XNOR Y, so while Cin bar constitute with X XOR Y, and of course these two XOR and XNOR are complement to each other. So we write this XNOR in terms of XOR like this to further get a more compact form like this, because if we are assuming X XOR Y as A and C as B, then again we will get this expression which is XOR output expression. Further, we replace back the assumed value in this expression, so we'll get the S expression as Cin XOR X XOR Y. So this is our S expression, we can say. And finally, the Cout expression can be written as X Cout is equal to Xy plus Y Cin and X Cin. So these are the two final Boolean or reduced final Boolean expression for implementing the full adder circuit. Uh, as you can see, these expressions required one XOR gate in which the inputs are X, Y, and Cin. So we'll implement our S expression in this way. And at the same time, the Cout expressions can be further. And this is a SOP expression in which there are uh, three product terms which are getting odd with the two odd operation are there. So to implement this SOP expression, we required AND OR logic. So in the first two level AND OR logic, in the first level we implement all the product term, and the output of those product terms will get it some using the OR gate expression like this. So we'll implement in this fashion. So this is the implementation of our full ladder circuit. And there is another way to implement our full ladder circuit, and to do that we do some small arrangement in the Cout expression, because as we can see the S expression is same finally, which we have got in the form of X bar Y and Cin. So this expression X bar X XOR Y XOR Cin, and the Cout expression can be written as in this form by taking some variable common like this Cin within bracket X XOR Y plus XY. The use of writing this expression is just to take help of some standard logic gate to implement this. So here you can see that we implement this S expression not by using the single XOR gate, but we are taking two XOR gate in which the two input two XOR gate, in which in the first XOR gate we are taking the input X and Y, so that we will get the output X XOR Y, and this X XOR Y output will go to the input to the next XOR gate, and then in that second XOR gate we are considering the input Cin as the second input. So finally we will get the S is equal to X XOR Y XOR Cin, which represents the S or the sum expression. Now we tried the purpose of writing the Cout expression in this form was just to get the input, means first because here are the two terms, you can say first term is XY and another is Cin XOR Y. So the first this XY term can be get by taking the input from XY and pass it through the two input AND gate, will get the XY term, and the second term, which is the Cin and XSY, we will get it from here, because this is the X XOR Y and this is the Cin line. So if you get it passed through the two input AND gate, you will get this term Cin XOR. And finally these two terms are getting summed with OR gate. So you can use two input OR gate and taking the output of these two AND gate and provided it to the input to this two input OR gate, you will get the Sout expression is equal to Cin XOR Y plus XY, like. Now interestingly, if you observe this implementation of a full adder circuit in this way, you will surprised to know that this actually the first block is actually represents half adder circuit. Similarly, the second block can also be represented as the half adder circuit. So that's why what we can conclude with this implementation, that if we are using two half adder circuits, then we can with a two half adder circuit and one extra XOR gate, we can implement our full adder circuit. So this entire implementation can be diagrammatically represent in this way also. We are having two half adder circuit and one OR gate. So in the first half adder circuit, we are taking input XY, and these output of S and C will further move to the next stage half adder circuit as input, and one input, and the second input to the half adder circuit is C in. While the the carry which is initiated in the first by the first half adder circuit as well as the second half adder circuit will pass through the OR gate to get the C out expression, and final we will get some expression as which is equal to, and this expression is equal to X XOR Y XOR C in, and the C out expression is C in X XOR Y plus XY. So this is the block diagram representation of full adder circuit, which can be implemented using the half adder circuit. Next, we can also implement our half adder circuit using the NAND NAND logic, and by that this implementation shows that how you can implement your half adder circuit using the NAND gates. So this is all in this video. Further, in the next video, we'll try to see other combinational circuits which are based on the same design approach. Thank you. Thank you so much.